Everyone. Welcome to another module in Communication System 2 course. In this unit, we discuss principles of spread spectrum modulation with emphasis on direct sequence and frequency hopping techniques. In a direct sequence spectrum, two stages of modulation are used. First, the incoming data sequence is used to modulate a wideband code. This wideband code transforms the narrowband sequence into a noise-like wideband signal. The resulting wideband signal undergoes a second modulation using a phase shift technique. Uh, in a FHSS technique, a frequency hopped spectrum technique, on the other hand, the spectrum of a data modulated carrier is widened by changing the carrier frequency in a pseudo-random manner. In both the cases, in both the types of spread spectrum technique, the data is widened by changing certain aspects in the carrier in a pseudo-random manner. And hence, for both their operation, both of these techniques rely on the availability of a noise-like spreading code called pseudo-random or pseudo-noise sequence, PR or PN sequence in short form. Since such a sequence is basic to the operation of spread spectrum modulation, it is logical that we begin our study by describing the generation and properties of a pseudo noise sequence. It's a heart of the spread spectrum technique. A feedback shift register consists of an ordinary shift register made up of M flip-flops and a logic circuit that are interconnected to form a multi-loop feedback circuit. At each clock pulse or each tick, the state of each flip-flop is shifted to the next one down the line. With each clock pulse, the logic circuit computes a Boolean function of the state of the flip-flops. The result is then fed back. The result is then fed back to the input to the first flip-flop, thereby preventing the shift register from emptying. We will make use of a non-systematic shift register. In coding theory, a systematic code is any error correcting code in which the input data is embedded in the encoded output. The input data itself will be available in the output in case of systematic shift registers. Conversely, in a non-systematic code, the output does not contain the input symbols. We can quote few examples for systematic codes. Checksums and hash functions combined with input data can be considered as systematic codes. Convolutional codes are implemented as either systematic or non-systematic. Non-systematic convolutional codes can provide better performance under Viterbi decoding, which we have studied in the last unit. Feedback shift register is said to be linear when the feedback logic consists entirely of modulo 2 adders. In such a case, the zero state is not permitted. We say so because for a zero state, the output would consist of entirely of zeros. We try to avoid such cases. And as you can see, it's a feedback shift register, and there exist feed forward shift registers as well. However, for pseudo random sequence generation, we are going to make use of feedback shift register only. Uh, uh, and hence, you can say consequently, the period of PN sequence with M flip-flops cannot exceed 2 power M minus 1. When the period is exactly equal to 2 power M minus 1, the PN sequence is called a maximum length or ML sequence or simply M sequence. Okay, the shift register that we will be using to generate maximum length sequences are of LFSR nature. In the sense, they are linear feedback shift registers. In short form, these are known as LFSRs. Now consider the linear feedback shift register as shown here, involving 3 flip-flops. the input S naught applied to the first flip-flop is equal to the modulo 2 sum of S1 and S3. It is assumed that the initial state of the shift register is 1 0 0, read from left to the right, 1 0 0. Then we can easily find out the sequential outputs or sequential states of these shift registers. If we start with 1 0 0, for next tick of the clock, this 1 will be shifted here, 0 will be shifted here, and the input of the first shift register would be modulo 2 addition of S1 and S3, which is another 1. And hence we can easily find out the sequential states of the shift registers. Starting with 1 0 0, the next clock pulse you'll get 1 1 0 as the state of the shift register, and then it would be 1 1 1, and so on. And after certain number of states, you would get back the original state of the shift register. So as we told, the period of this sequence is 2 power m minus 1. M here is 3, and we expect the state should repeat after every 7 sequences. Say 1 2 3 4 5 6 7. After 7 sequences, you will get 1 0 0, which is the original state of the shift register. So we can see that output sequence which gets generated due to this particular connection of the feedback shift register is 0 0 triple 1 0 1, and hence again it is 0 and it repeats itself. The output sequence is taken out from the final shift register, which is S3, and these are the last bits of the sequences. Okay, but please note that the choice of 1 0 0 as initial state, we have chosen 1 0 as 0 0 as initial state, is just a random choice. Any of the 6 permissible states could serve equally well as an initial state. Only thing is we can pick any this as initial state, and we can keep on shifting it right and performing modulo 2 addition and feeding it back to first shift register and performing it again. Nevertheless, the period of the sequence would be 7 itself. Okay, ML sequences have many of the properties possessed by a truly random binary sequence. We expect these maximum length sequences to mimic a pure random binary sequence, because we are in the process of generating pseudo-random codes or pseudo noise codes, and hence we expect the output of maximum length sequences or the maximum length sequences themselves should truly mimic random binary sequence. A random binary sequence is a sequence in which the presence of binary symbol 1 or 0 is equally probable, and hence it is called as random. Some properties of ML sequences, let's see whether they mimic true random nature of original binary sequence or not. And we know that the period is 2 power m minus 1, where m is the length of the shift register. This is one obvious property of ML sequence. There is another property called as balance property. It's called so because the number of ones is always one more than the number of zeros in each period of a ML sequence. In case of a truly random binary sequence, the presence of symbol 1 or symbol 0 should be equally probable. It's always close to such property, which is called as balance property. However, number of ones will always be one more than the number of zeros. Next property called as run property. Among the runs of ones and zeros in each period of a ML sequence, one half the runs of each kind are of length 1, 1/4 are of length 2, 1/8 are of length 3, and so on, as long as these fractions represent meaningful numbers of runs. Okay, this property is called the run property. By a run, we mean a subsequence of identical symbols, either ones or zeros, within one period of the sequence. The length of this subsequence is the length of the run. For a ML sequence generated by LFSR of length m, the total number of runs is n plus 1 by 2. Okay, n, capital N, is the period. So the total number of runs is n plus 1 by 2, where n is equal to 2 power m minus 1. So let me try to explain a little more about this statement. If I go back to the sequence that we generated earlier using this particular structure of LFSR, this was the succession of states and this was the output sequence. If you carefully observe this output sequence, we say a run, we mean by a run as subsequence of identical symbols. Say if a run length is 1, it is just 0. So if I take 0, it is repeated again here as 0. So we cannot take it as a run. So 1, again it is repeated as 1 here. So we cannot take it as a run. So it is different for the sequence here 1, 0, 1, 0. So this is of the length 4, which are run length as 1, as these are length run 1 means these are distinguishable symbols 1 and 0 alternatively. As per the property, one half the runs of each kind are of length 1. So here the run length is 1, one half in the sense 8, we can say the 7 plus 1 by 2, 8 by 2, that's 4. The 4 is the run of length 1. Then next is 1/4 is a run are of length 2. So if I take length of 2, which are identical symbols of zeros or ones, it could be either 0, 0 or it could be 1, 1. So if you carefully look at that, 0, 0 and 1, 1 appear only twice in the sequence if I take combination of them. So if the if the run length is 2, there are two such cases here, 0, 0 and 1, 1. And hence, by the statement of run property, 1/4 are of length 2. 1/4 here is 8 by 4, which is 2. The length 2 which is the run length. There are two such cases here. And finally, 1/8 are of length 3. In the sense, there should be similarity between the symbols of run length 3. So I can say 1, 1, 1 is a sequence of similar symbols as 1, 1, 1, which are of length 3. It appears only once in a period. So we should consider just one period and find out such runs. And hence, it's the number of appearances of these run lengths 1, 2, 3 is a fraction of 1/2, 1/4, 1/8 and so on. Okay, so that should be very clear by this example that we have considered earlier. And finally, there is an important property of maximum length sequence called as correlation property. The autocorrelation function of a maximum length sequence is periodic and binary valued. Okay, this property is called as correlation property. I will try to understand more about this correlation property. As mentioned earlier, the period of maximum length sequence is defined as n is equal to 2 power m minus 1, where m is the length of LFSR. Let binary symbols 0 and 1 of the sequence be denoted by the labels +1 and -1 respectively. This is the waveform called as C of t denote a waveform of the maximal length sequence of capital N is equal to 0. This was one of the sequence that we generated earlier. In the earlier example, we generated a sequence of 0, 0, 111, 0, 1, 0 and so on, which repeats after 7 bits of period. Okay, so we have taken the same example 0, 0, 111, 0, 1, again 0, 0, 111 and so on. Okay, where where TB is a bit period which represents actually the length of a period, which is capital N times TC, where TC indicates the duration assigned to binary symbol 1 or 0 in the maximal length sequence, where TB is a period of the waveform which repeats for n times of TC. Okay. The autocorrelation function of this particular C of t can be calculated by using the formula RC of tau as 1 over TB with a period minus TB by 2 to plus TB by 2 C of t times C of t minus tau. So this can be found out mathematically, and we can try to plot the waveform as well, where that lag tau, the tau is in the interval of minus TB by 2 and plus TB by 2. Okay, applying this formula onto C of t, we can readily get an equation, a mathematical expression for autocorrelation function as 1 minus n plus 1 by n tc times modulus tau for tau less than or equal to plus or minus tc, and for the remainder of the period it's minus 1 by n. So with that we can plot here, as it clearly states that between minus tc and plus tc there is a value called as 1 minus n plus 1 over ntc. So this is a triangular shape that resembles that, and for remainder of the period it's flat minus 1 by n, which is represented as minus 1 by n in the picture which describes the autocorrelation function. Okay, this is plotted for the case m is equal to 3 or for period n is equal to 7 that we have taken earlier. Okay. From Fourier transform theory, which you have studied in your earlier courses, we know that the periodicity in the time domain is transformed into uniform sampling in the frequency domain. This interplay between the time and frequency domain is born out by the power spectral density of the maximal length wave C of t as well. Then specifically taking the Fourier transform of R of tau, we'll get the sampled spectrum as SC of f by equation 1 by n square del of f plus 1 plus n over n square summation minus infinity to plus infinity, where n not equal to 0 is included, n is equal to 0 is not included, which has sinc square n by n times del of f minus n over ntc. This is the expression which is obtained by taking Fourier transform of autocorrelation function. So the Fourier transform of autocorrelation function is known as power spectral density, which is plotted here. Okay, uh, uh, if you try to compare this power spectral density with that of a binary random value, which is obtained in stochastic processes, you might have studied in your earlier courses as well, that corresponds to such a waveform. As you can see, there is much closer association between these two power spectral densities. This is a power spectral density of a random binary wave. This is a power spectral density of maximum length sequence that we obtained. So we are in the process of saying maximum length sequence. The maximum length sequences resemble very close to the random binary waves, and hence we want to generate pseudo-random codes or pseudo-noise sequences. We'll try to draw certain important observations here. The autocorrelation function of random binary sequence is very similar to that we have obtained for maximum length sequence from RC of tau. It's somewhat similar to that of random binary wave. The waveforms of both sequences have the same envelope, okay, which is sinc square f of t for their power spectral densities. However, the fundamental difference between them is that whereas the random binary sequence has a continuous spectral density characteristic, the corresponding characteristic of a maximum length sequence is discrete, consisting of delta functions spaced 1 over ntc hertz apart. So the separation between these discrete delta functions is 1 over ntc. Okay, so that is only the difference between these two spectral characteristics. Okay, as the shift resistor length m are equivalently the period capital N. So as capital N of the maximum length sequence is increased, the separation between delta functions will also be very, very small, and hence those will resemble more similar to the random binary sequence, and hence Indeed, in the limit as capital N tends to infinity, the two sequences become identical. Okay, when capital N made extremely large. However, the price paid for making capital N large, remember capital N is nothing but 2 power m minus 1. The price paid for making capital N large is an increasing storage requirement. Capital M increases in the sense number of shift registers will also increase, which imposes a practical limit on how large capital N can actually be made in practical applications of spread spectrum modulation. So this ends with a good the properties of maximum length sequences. We'll try to explore more into these properties and try to draw more conclusions about these set of pseudo noise sequences.